So we'll talk about now nearest neighbor approach and then support vector machine. So from the name you understand that will have some training data. From there, in the k nearest neighbor approach, we don't build any model. We will memorize all of this training data. When the test data comes, we'll compare our test data with all of the training data points and find the closest one and assign the class level, whatever the closest one we have for the test data. So the nearest neighbor method approach is this: store all the training examples, and given a new data point x prime, so we will define some sort of closeness. Closeness can be defined by using Euclidean distance or cosine similarity, something like this. So find the nearest training example xi and yi to x prime. Again, recall that x prime is a test example, test data. So and then if this is the training example which is closest to x prime, so basically x prime is closest to xi. So then xi dependent variable will be yi. So that's the idea here. So what is the problem with this approach? So here again, there is a demo. You can see it from that link from the Stanford. But let's say, just to give an example, in a two-dimensional space, you have let's say this is a data point, test data point like this, and I want to predict the class level. So this is all rest of the data points, all of my are training examples. So what I will do, I will calculate this, and I want to run it for k equal to 1 nearest neighbor. K equal to 1, and I run it 1 nearest neighbor. So I want to run it for 1 nearest neighbor. So what I will do, and recall that I have 100 training examples. Okay, so I'm saying k nearest neighbor where k equal to 1, I want to do it. And I have 100 training examples like this. So what I will do, intuitively, can you think? So we will store all the training examples. So this is also known as a lazy learner. So I will store all the training examples. When the test data comes, I will try to compare it with all of the training examples. Let's say my test data is x prime. So I will compare x prime with all the 100 training examples. So in that case, I have to estimate the proximity. So in this case, let's say I will do the Euclidean distance and find the 1 nearest neighbor. So what I will do, I will calculate the x1 and the point 1, the distance between x1 and the point 1, distance between x prime and the point 2. So point 1, point 2, all the way point 100. These are my training examples. So that means I will do what? I will calculate the distance x prime and p100. So this will give you what? It will give you a number, right? It will give you, let's say, 3.7, 3.9, maybe 0.0001, something like this. And then what you will do? You will sort this distance in increasing order or decreasing order. Find the 1 nearest neighbor. Yeah, increasing order. And choose the topmost one. If it is k equal to 3, I will choose the top 3. And then, so let's say if I choose the k equal to 1, then what will happen? So I'll find the closest one. And then closest one, let's say the pi, whatever the class level it has, then I will say that x prime will have the same class level. So it's a very simple approach. Yeah.
Why wouldn't you look for the lowest number if it's the distance from the sample?
Lowest number. Okay, so distance between the x prime and the training point, right? So I'm looking for nearest neighbor from the training points, closest one. So in this case, this is a distance. So I need to look for the closest one, means the minimum distance or the smallest distance, yeah. But if it is a similarity, you're right. We may need to choose the highest similar one. If it is instead of distance, if you represent them in a similarity values like cosine similarity, in that case, you will choose the most similar one. So now if I do it for k equal to 3, then what will happen? 3 nearest neighbor. So let's say 3 nearest neighbor, we observe that P5, P7, and P9, these are the 3 nearest neighbor with respect to x prime. And P5 represents positive class, P7 represents negative class, P9 represents positive class. So which class x prime will be assigned? Plus, due to the majority voting. Or you can do the weighted voting also based on the distance. So you have a distance P5 and x prime, right? If this one is shorter, then this positive will carry more weight in the voting process. So this, you can say, so basically in the voting process, you can do the weighted vote. So weight will come from the distance. Lower the distance, it will carry the higher the weight, something like this. Okay, so I tried to tell you that the learner, all this supervised learning can be 2 types. One is called lazy learner, other one is called eager learner. So learner can be 2 types. Eager learner means you try to build the model immediately and so on. And lazy learner means we don't learn anything from the training data. So k nearest neighbor is lazy learner because we memorize all the training data. When the test data comes at that point we try to do the prediction using the raw training data. So that's called lazy learner, k nearest neighbor. On the other hand, decision tree is a eager learner. Naive Bayes also eager learner. In the one Thursday, you will hear about there are other ways learner or learning technique can be categorized. One is called generative model, other one is called discriminative model. But that you will hear on Thursday. Okay, so now the question is when you want to apply. When you have a fewer dimensions or feature set, k nearest neighbor will work very well. But the advantage is no training is required, but it is a problem also because when the test data comes, it will take a lot of time to do the prediction. So can you give me an idea how we can improve the k nearest neighbor performance? If I have 10,000 points and every test data comes, I need to compare it with the 10,000 points, right? Right, very good. So you need to first group this training data using some clustering algorithm, build the clusters. And when the test data comes, you will compare each of these clusters. And this clusters is built based on the class level. So this is, let's say, class level 1, and from there you build certain clusters, something like that. That way you can speed up. But again, clustering is an expensive process also, but that will be done offline. You will build a cluster one time and hoping that that type of cluster will hold. It can be used for a while. Okay, so there are other, and then another problem is a high computational cost. Classification will take time because it's a lazy learner, and it is difficult to find the optimal k also. Okay, then last but not least, shallow learner, what do you call it, SVM, support vector machine. And it was before deep learning comes into play. You know that nowadays, if you go any machine learning conference, people will talk about deep learning, and deep learning solves all problems, they claim. I'm not saying it also, but deep learning requires a lot of training data and so on. It works very well for the images, and we'll talk about that, or that text also. We'll talk about that on Thursday and Friday. Now, let's talk about the support vector machine. Is another way to do the classification, and is also a eager learner. So we'll have a training data. From there, we build the model. It works very well when you have a binary data set or binary class. It can be extended or also in a multi-class setting. So in this presentation, first I will focus on the binary class, or when we have two classes. From there, we want to build the model. So here, without loss of generality, we have a two-dimensional data points for negative instance and the positive instance. And you can see this is a training data, and for this case, what we want to come up with a hyperplane that will separate the positive instance from the negative instance. In this case, this is a two-dimensional data, so it will be a line that separates positive instance from the negative instance. Now, in an n-dimensional space, it will be so in a two-dimensional space, it will be a y equal to mx plus c, that type of equation. You know that y equal to mx plus c. That type of equation can separate the positive instance from the negative instance. But n-dimensional space, it will be something like this: wtx plus b. X is the data points or independent variables of values, and then w is the weight we want to learn, or the coefficient, and the b is the bias. So in this case, we assume that in this binary classification problem, we assume that data will be linearly separable. There will be a line that separates, or hyperplane that separates positive instance from the negative instance. Now, so our goal is to find the hyperplane such that from the training data we can do this type of learning. And when the test data comes, we will plug in the x prime, and we'll already know the wt and b. From there, whatever the values we will get, and from the sign we will determine the class level, whether it's a positive class or negative class. Now, if your data points have something like this, in a two-dimensional space, so we have a red class and the blue class. Do you think any hyperplane, in this case any two-dimensional space, any line can separate red class from the blue class? The answer is no. So that's why this data is not linearly separable, it's linearly inseparable. So in case of not linearly separable, in case of this case, non-linear case, what we do? We transform this raw data into a higher dimensional feature space. So if it is a two-dimensional data points, we will convert that two-dimensional data points into a three-dimensional data points, and using this phi. And then in a higher dimensional space, the points will be linearly separable, and we can build the model. So here is what I try to say. So if you have a two-dimensional data points and x1 and x2, and we will transform into a higher dimensional space. And higher dimensional space will be like this: z1, z2, z3, and z1 will be derived from using x1 square, z2 will be derived from this, and z3 will be something like this. And now each data point in this case will be described by two features. Now it will be described by, in a higher dimensional space, it will be described by three features. And they will be linearly separable. Then you can come up with a decision boundary to separate them. So now let's talk about the basic one first, when the data points are linearly separable. So we define the margin to be so margin will play some role. So now let's think about this. We have a two-dimensional data points, x1 and x2. And this is a positive red instance, and this is the blue instance, blue class and the red class. And now I want to come up with a separator that will separate positive class from the negative class. So what will be the margin? Margin means which separates positive class from the negative class. The margin is twice the distance of the closest data point to the classifier. And SVM, the property of the SVM, this is the very basic idea SVM uses. It tries to maximize the margin. There is a reason why you want to maximize the margin, is this. Just think about this. This is in some instances, positive class and negative class. So one decision boundary will be something like this. Another decision boundary will be something like this. So there are many ways you can come up with the decision boundary, right? So I'm saying, we call it, this is one decision boundary, and there is another decision boundary from your training data that will separate positive instance or blue dot positive instance from the negative instance. Now the question is which decision boundary you will use. So for that we define the margin of a classifier as the width that the boundary could be increased before hitting a data points. So in that case, it is better to make sure that the margin will have this width should be bigger. That's the very basic idea. So this is a line, and that line, if I move in this direction, it touches the first, what is this class? Whatever the, okay, blue or the plus, let's say this is a plus, positive class, this is a negative class. It touches the negative class here, and in this case it touches the negative class here. And then the hyperplane will be something like this. So in that case, this is the margin, right? So this bigger the margin is better, because that way you can avoid, if it is a very thin, then that's not good. Thicker margin is better. So that's the very basic idea here. And this case, keep in mind that these are the training examples, right? Not all training examples will play a role in your SVM classification process. Only few points, few training examples will play a role. And those few points will be known as the support vectors. Basically, these support vectors which are closest to the decision boundary. So what I'm trying to say, in case of support vectors, there are a bunch of training examples we are going to use. Using these training examples, we will build the decision boundary. Not all of the training examples will play a role to build the decision boundary. Which are closest to the decision boundary, these are the points, training points that are closest to the decision boundary. They will play a role to construct that decision boundary. So there is a chicken egg problem. Now, if we know this decision boundary, then we can easily estimate these are my support vectors, right? So I said this point is not a support vector, is not an important point, because this point is far away from the decision boundary. And that will not have any impact to generate the decision boundary. On the other hand, these points will have an impact to generate the decision boundary. Now the question is, how do you construct the decision boundary? Because we don't know that decision boundary in advance. What do we know? Only the training points. So from this training point, some of the training points will play a role to construct the decision boundary, and some of the points will not play any role. So whichever points will play the role, those points will be known as a support vectors. So in other way, you can say support vectors are the points that the closest to the margin, or that will touch, if the decision boundary moves, that the points will immediately touch those points, training points. So do you have any questions so far? Yeah?
One point of curiosity is this seems like if it has noise in the test data,
Yeah.
and the training data, sorry.
Yeah. So there will be, at this point, I assume that there is no, the training data points will have any noise. If there is a noise or error in the training process, there is a additional formula I'll show you that takes into consideration that fact. Okay, now in this case, keep in mind that X is your data points and W is the vector representation, but it will be if you have an n-dimensional points, we will have an n number of weights will be associated. This will be a vector also, and B is the scalar value. So if you have a two-dimensional data points, it will be something like this. So now, if I calculate the distance of a point x to a line wx plus b, this is a point wx plus b equal to 0, then how do you calculate the distance? From your in the 11th grade or 12th grade or in the university undergrad, what is it called? The distance calculation, wx plus b equal to like this, right? Okay, so here what I meant this. So basically I'm trying to determine the margin thickness. Okay, so if I say Wt x1 plus b equal to 1, Wt x2 plus b equal to minus 1. And if I subtract this, Wt x1 minus x2, 2, and x1 minus x2, 2 divided by Wt. Okay, so here the point I'm trying to make, Just think about this. I want to determine the margin. And the idea here is the decision boundary should be as far away as from the data of both classes as possible. And we should maximize the margin M. That's our goal here. What is margin here? Margin will be defined, let's say one point is here, another point is here. And if you calculate the distance, Wt x plus b equal to 1. So in that case, it will be, if x1 is in the positive side, it will be something like this. If x1 is in the, x2 is the negative side, it will be something like this. And now if I subtract this two equation, x1 minus x2, what will be the distance? Equal to 2. Now if I subtract this 2 over, so if I calculate the difference between x1 and x2, basically the perpendicular distance between 2 points, that one of them sits here and one of them sits there, then that distance, the difference will be x1 minus x2 will be 2 over w. So that's nothing but the margin. So now our goal is to maximize this margin. So we said we want to make the margin thick. So keep in mind that we have a training data points x1, x2, xn, and yi at the class level, either positive class or negative class. Is a binary class we are talking about. And each of this xi is a data points. It will be a vector. The decision boundary should classify all the points correctly. And now when yi equal to minus 1, we wish wx plus b equal to less than 1. And when yi equal to 1, we want wx plus b will be greater than 1 from the training data. That way we want to learn w and b. And for support vectors, we wish yi times wx plus b equal to 1. So basically, when you have this, goal here is to minimize this. If you remember, our goal is to minimize. Goal here is to minimize this, right? So minimum, this means maximum. I'm sorry, I say we want to maximize the margin, right? We want to maximize this, right? So if I want to maximize this, that means if I reverse it or inverse it, then we want to minimize this. Do you agree with that? So if I say that's our maximize objective function, we want to maximize it in order to learn. Our goal is to learn w and the b, right? So in order to learn w and b, we need to maximize this. When we want to maximize this, I can say we want to minimize this. That's the same. Now the constraint is yi times wtxi plus b greater than or equal to 1 for all I. When xi is a positive class, then I know that yi will be positive level, right? Plus 1. So plus 1 and wtxi plus b, that will be greater than 1. It will be greater than 1. So positive. And then when I is a negative class, let's say I is a negative class, then what will happen? If xi is a negative class, training example is xi training level is negative. Xi level is negative or yi is negative, then what will happen? So wtxi plus b equal to less than or equal to, less than minus 1, right? And then and yi is also minus 1. So multiply both, it will make you yi times wtixi plus b greater than or equal to 1. So this is minus 1 and this is greater than or equal to minus 1. That 2 minus 1, 2 negative will make you positive. That's what I'm saying. Okay, now there are a lot of maths are involved. I'm not going to go through the details of the math, just I want to give you an idea how this thing works. Okay, so our goal is to minimize this, and where the constraint is this. Do you agree with that? Okay, now, so that basically what we will do, our goal is to minimize these objective functions. From there, we will plug in this, and each of this yi or each of these xi training examples will have a Lagrangian multipliers. So this is alpha I, and our goal is to minimize the whole expression where such I alpha I will be greater than or equal to 0. So the idea here is this is the training examples and the training class level, and then each of the training points will have a Lagrangian multipliers. And now Lagrangian multipliers will be either 0 or greater than 0. That's the things we can have. And our goal is to minimize this whole expression. And then, how we can minimize this objective function? In calculus, what do? We take the partial derivatives. Del, I will try to minimize it with respect to this. Del objective function LP, del W, and del LP, del B. So once you take the partial derivatives, and then after simplification, you will see that the expression becomes like this. So alpha I, we need to, and there is a before it was a minimize this, and after simplification, all of this, you will see minus. That's why we need to maximize it. Alpha I minus this. And good thing about this equation is it doesn't have any W. It has only no W, no B. So we need to know alpha I and alpha j. We know yi, yj, xi, xj. These are the training examples. But we don't know alpha I, alpha j. So we only know alpha I should be greater than or equal to 0, and this is the condition needs to satisfy. So now once we solve this equation using the quadratic programming, we solve this equation. That way, for each of the training points, we get the alpha I. Each of the training examples, xi, we will get the alpha I. Now, when the test data comes, we want to do the prediction. Let's say my test data is x, and now the question is, we only know alpha I, and from the alpha I, we can easily calculate the W. That I will show you in a minute. So here, how we calculate the W can be recovered from this. Alpha I times yi times xi. Yi and xi are y is the class level, xi is the independent variable, and the alpha I Lagrangian multipliers, we learn it. So that multiply and give you the W. So once you know the W, then what will happen? So this is W will be stated like this: alpha I xit, and alpha I we solve it using the quadratic programming, and then x is the test data. We plug in here, and that gives you some numbers. And then if this number is greater than 0, then we call it positive class. Is less than 0, we call it negative class. So that's the idea. And here we take the dot product between the test point x and the support vectors xi. Okay, one of the key points I never mentioned. In this quadratic, when you solve this equation using quadratic programming, you will observe that many points, many training examples, their support vectors will be alpha I value will be 0. If alpha I value is 0, that means those points will not serve as a support vectors. The points, I said some of the points will, in a training process, each point will have a Lagrangian multipliers or alpha I. So those points will serve as a support vectors. Their Lagrangian multipliers, alpha I, will be non-zero. That's the key point you will observe. And those points will contribute in your, so those points will contribute in your, So here I said I is a support vector. That means those alpha I will be non-zero. They will contribute in your prediction or in your test calculation. Okay, now, so the point I'm trying to make here, in this case, the second equation, so dual problem. So there, this objective function is stated in terms of alpha I only, and if we know W well, if we know W, then all we know all alpha i's. If we know all alpha i's, we know the W. So it's a chicken egg problem. The original problem is known as the primal problem. The objective function of the dual problem needs to maximize. The dual problem is therefore like this, what I told you before. So our goal, we solved this equation using the quadratic problem. Quadratic programming will be used, that you don't need to know, but the tool will give you the solution already. And then from there, you can estimate the W. So the key point is this: many of the alpha i's will be 0. W is a linear combination of a small number of data points. This sparse representation can be viewed as a data compression in the construction of the KNN classifier. Xi with alpha, with non-zero alpha I will be known as a support vectors. This is the key points I'm trying to make. So when you have a training examples, that training examples has non-zero alpha I, those points will serve as a support vectors. And the decision boundary will be based on this points only, will be determined based on these support vectors. And let's say Tj is the indices of the S support vectors, then I can say that W can be derived from this, only this support vectors. So non-support vectors will not contribute for the W calculation. And once you have a W, then from the test data comes Z, and you can estimate the class level. If the sum is positive, then it will be a positive class. If the sum is negative, it will be a negative class. So again, what I tried to tell you before, so we have total how many instances we have? Total 10 instances, 10 running data points we have. And each data points will have a Lagrangian multipliers alpha, right? And then this is a two-class problem, and we need to estimate W. So what we will do, for each points, using the quadratic programming, we will end up with the alpha or the Lagrangian multipliers. So these are the points you can see Lagrangian multipliers are 0. So therefore, these points will not serve as a support vectors. On the other hand, alpha 6, alpha 1, alpha 8, these are the points will serve as a support vectors because their corresponding Lagrangian multipliers will be non-zero. And this alpha will contribute in W calculation. That I'm trying to make. This is the key point. And then one of you already pointed out that how about if there is an error in the training data. So if there is an error, let's say most of the data points fall into this, and this might be the correct decision boundary, but one of the points falls into this area. Then in that case, we will allow some slack variable. So the decision boundary will be, instead of WTX plus B equal to 1, it will be 1 minus xi, what is it called? Xi. So in that case, if it is a positive example, it will be 1 minus xi. And if it is a negative example, 1 minus 1 plus xi. So that way, we will add the noise or the erroneous data. So xi are the slack variables. In optimization, if xi equal to 0, there is no error in the training process. And our goal is to minimize this, and then with this additional error constraint will be added. And our goal is to, on the optimization function, our goal is to minimize this with this constraint. And then there is, then if you do the transformation and everything, you will see that xi will be eliminated from the equations. Only the equation will be, after the Lagrangian multipliers and all this simplification, equation will be like exactly this. When you, only constraint will be, this will be changed. Alpha I will be greater than or equal to 0, but less than some constraint C. And that constraint C will be defined from previously where we said, okay, so this will be the C will come into play. So the C will be xi greater than or equal to 0 and less than C. So that way the additional constraint will be added. But the other expression, the whole alpha I, the quadratic equation, there will be no zi there. Ji will be eliminated. Now, so that's a nutshell. I just tried to tell you how the support vector machine works. I want to tell you a little bit how we can extend that problem in a multi-class classification, more than 2 class. So if I have a 3 class, like blue class, green class, red class, and I want to train my classifier using SVM. So one approach is, why don't you do one versus all, or one versus rest, they call it. So we have 3 classes, right? So first case, we will train it with the green class versus rest. Rest will be the blue class and the red class. So that way we will train our classifier. So support vector will come up, the training will come up like decision bound will come. And then second case, we'll train it with the blue class versus rest. So the decision bound will come up with something like this. And the third class, we'll train it with the red class versus rest. And the decision boundary will be something like this. So now when the test data comes, we build 3 models, right? Because we have 3 classes, one versus rest, 3 classes will build. And the test data points, let's say, each of them will come up with a prediction. And then the test data point x will be assigned to class k prime, where this value will be the maximum. Or alternatively, you can do a pairwise. Basically, you will calculate the classifier between a blue class versus red class. One model you will build. Another model you will build, what is this class? Green class versus red class, model 2. And the third model will be, what will be third? Okay, there are 3 classes, right? So 1 versus 1. So there. So I will build model 1, which will be green versus red. Model 2, which will be red versus, what is it? Red versus blue. Model 3, blue versus green. So this way we build the 3 models. When the test data comes, each of the model will do the prediction and will apply the majority weighting to make the decision. So that's called 1 versus 1. And the last but not least, I said if your points are not linearly separable in the original space, what you will do? So we will apply the kernel trick. And so the kernel trick is map the problem from the input space to a high dimensional space. We call it feature space. And by doing a nonlinear transformation using a special function called the kernel, and then when the points are linearly separable in a high dimensional space, we apply that typical support machine learning, typical SVM to do the classification or build the model. So here is the idea. We will transform. Here we cannot separate this red dot from the blue dots in a single dimensional space. I'm sorry. This in a 2-dimensional space, these red dots cannot be separated by a line or hyperplane from the blue dots. So what do we need? We need to transform these 2-dimensional points into a 3-dimensional space, and then in a 3-dimensional space, we can come up with a hyperplane that can separate positive instance, that can separate red points from the blue points. So here the idea, we will convert original feature space to the original data points from the input space to the feature space where the points can be well separated and so on. Now the problem is, if you do this conversion explicitly, you will take each data points and convert it into the high dimensional space. That will be computationally very expensive. So that we don't want to do it. So for that, in order to avoid that expenses, we can use the kernel trick. The general idea for the kernel trick is the original input space can always be mapped to some higher dimensional feature space where the training data is separable. And again, the recall that this is our main objective function we try to maximize in the support vector machine case. This is the Lagrangian multipliers multiplied by alpha I, alpha j, the yi, yj's corresponding Lagrangian multipliers times xit, xj, right? So this is your transpose. And so here the good thing is we take the inner product or the dot product. You know the dot product? What I meant, if I have a 2, 3, 5, each data points is described by, let's say, 3 dimensions. Dot product is 1, 5, 7. So what will be the dot product between this xi dot xj? 2 times position wise, right? 2 times 1 plus 3 times 5 plus 5 times 7, right? So you don't need to put a plus sign. You just say. So that way I can calculate the similarity between, I can do a dot product, right? Okay, so what I'm trying to say here, when you have a dot product like this, you don't need to do a complex calculation. You can just do the position-wise multiplication. That way you do the inner product or do the simple calculation. So as long as if we can calculate the inner product in the feature space, we don't need the mapping explicitly. So that's our goal. So let me explain that in a minute. Suppose we have a 2-dimensional data points, x1 and x2, and we use the phi transform, the feature space transformation. So feature space will transform original data points as a 2-dimension, x and x2. And when you do the feature space or project into higher dimensional space, it will be something like this. Higher dimensional space, it will be stated like this: 1 comma second dimension will be root over 2x1, and in this case third dimension will be something like this, fourth dimension will be something like this, and so on. So now, here each of these data point x1 and x2 will map into very high dimensional space. Now if I take an inner product between these two feature space, so what will happen? So if I expand this formula, I said we have 1 root over 2x1, and then x1 square, then x2 square, root over 2x1, x2, right? And then 1 root over 2y1, y1 square, y2 square, root over 2y1, y2. So what it will produce? It will produce 1 comma 2 x1. So dot product, right? 2x1 y1 not plus comma x1 square y1 square comma x2 square y2 square comma 2x1 x2 y1 y2, right? So what I'm trying to say, you instead of take each point and convert it into explicitly like this and take the dot product, that one way you can do it. But that way each point you will map into the high dimensional space, then you will apply the dot product. which will be computationally expensive. Instead, we will use the kernel trick. So kernel trick in this case, between 2 points, if I need to calculate the dot product, I will use this. And what this is using, this is exactly same what we are doing here. This dot product, when you calculate the dot product or inner product, that produces this. And this is equivalent to this. And this is equivalent to this. And this is nothing but a KXI is the kernel trick that will take the 2 points, X and Y, and stated in terms of in this way. And if you expand it in original space, it will produce some numbers that will be equivalent to what you do in a projected space or in higher dimensional space. So the point I'm trying to make here, one way you can do it, you take each point, convert it into a higher dimensional space explicitly, then take the dot product. So that if you have 100 training points, you have to project it into the higher dimensional space first, map into the higher dimensional space, then you will do the dot product. So that we don't want to do it explicitly. What we want to do, we will take those points in the original space, applying the kernel trick like this, and that will automatically produce the result that we want to do it in the higher dimensional space like this. So for that, there are not all functions you can use. There are the kernel functions, certain kernel function you can use. So most widely used one is called Gaussian RBF, radial basis function. But you can use the polynomial kernel function where d equal to 2. Say, for example, it will be a part 2, or it can be more than part 2 also. So RBF usually works very well. That's what I'm trying to say. And then when the test data comes, test data now we know that WTX phi x plus b. Phi x is the x is the original data points. It will be projected into the projected space in the high dimensional space. Then what we will do? Alpha I we already calculated, the Lagrangian multiplier. So phi xit dot phi x, and that can be estimated using the one way you can estimate by doing the explicit projection. That we are not doing it. What we are doing the kernel trick here. So that can be estimated using the kernel trick that I described here. So using this kernel function, you can easily estimate in the original. In the original space means x1, x2 in the original space. That's the power we are using here. Okay, I don't want to take your time. I think you are bored already. So in summary, what I covered, a decision tree is a classifier in the form of a tree structure, and decision tree is a Eger learner, and it can, from the training data, we build the model, but it has sensitive with the overfitting. For overfitting, we use the pruning data. We do the pruning of the tree by using the validation data set. In naive Bayes, you know that it is based on the probability Bayes theorem and so on, but it has also weakness. It assumes that the attributes will be independent from each other, which may not hold in real life. And then we showed you the k-nearest neighbor, where when the test data point comes, we try to find from the training data, we try to find the closest match from the training data and then assign the class level. But it is a lazy learner. We don't learn anything there during the training process. And for SVM, it's based on the maximum margin. And there, only few training points will serve for the decision construction. Those points will be known as support vectors, and the rest of the points do not play that much role. They will be known as non-support vectors. And decision boundary is a support vector machine works very well for the binary classification, but it can be extended for multi-class classification problem also. And then I try to tell you that if your data points are not linearly separable in the original space, we can apply the kernel trick to map into the higher dimensional space. And using the kernel trick, we don't need to do any explicit transformation. We will use the original feature space to do for the manipulation and so on. That type of thing I covered so far. So now we'll go to the last. We'll go through the last lab. For today. So lab number 2.